All right, let's get started. So, yeah, how's everyone doing? About lab 1 homework? Good. Yeah, I see one student submitted lab 1 already, so which is very good. So feel free to submit that early. Okay. Yeah, and any questions for lab 1? General questions. Right, if you have a specific question, so feel free to ask me or the TA. So we can always, besides going to the lab, we can always have a Zoom meeting to discuss about the lab problems, okay? Okay, very good. So yeah, let's, oh, by the way, so I uploaded the lecture material already, except the video. Okay, so you can see the lecture slides and lecture notes for today. And let's have a brief overview of the previous lecture. So in the previous lecture, we start with talking about the non-periodic signals and how the non-periodic signals passing through a system. Okay, and the idea is that so we start from the periodic signal and then we introduce the nice Fourier transform, Fourier series, right? And so we only care about the complex exponential version of the Fourier series. And since there are a lot of nice property of the Fourier series, so we want to use the same thing for the non-periodic signal, okay? And we can extend the concept of the Fourier series to the non-periodic signal. Normally, the non-periodic signal is the energy signal, okay? And in this case, yeah, because it's not periodic anymore, it basically means that the period is infinity, right? If the period is infinity, then the fundamental frequency will go to 0, right? So in the frequency component, it will become continuous, right? So basically here we need to use a different base, so which is again complex exponential, but the frequency now is real instead of multiples of the fundamental frequency for the non-periodic signal, okay? And here since this is a continuation of the previous slide, so basically we talk about h of t, so which is impulse response of a system, meaning that when the input is delta signal and then the output is h of t, right? So h of t can represent a linear time invariant system. It can also represent a signal, right, where the input is a delta signal, okay? And by doing this, so we can define the Fourier transform, so which is like that. So we can derive this formula from the definition of the Fourier series, okay? Just by letting t0 goes to infinity or f0 goes to 0. Okay, and you can see the definition of the Fourier transform is very similar to the Fourier series, right? The form is exactly the same. The only difference here is this guy, right? So we have a f instead of f0, n times f0, and the integral limit. Now it's from infinity from minus infinity to plus infinity. So for the Fourier series, so that is within one period, right? That's the only difference. The format is exactly the same. Okay, and then we can define the inverse Fourier transform, which is given by this formula or this formula, right? It depends on what kind of frequency you use, right? If you use the normal frequency in hertz, then this will be the formula. And if you use omega, so omega equals to 2 pi times f, right? And then we have this formula, okay? The only difference here is that we have another scaling factor, 1 over 2 pi here, so which may not be desired. So in practice, we use that the most. Okay, and then normally for the Fourier transform pairs, we write that in this way. Okay. Okay, and here is a very important property for the Fourier transform operator. So it's a linear operator, right? Today we're going to use that quite a bit. Okay, so remember that. So basically, so now we have an example of just 2 signals, right? So then we can basically, linear operator meaning that we can move the operator inside, right, to each of the individual function, right? This means it's a linear operator. And we can extend that to infinite case, right? If I have an infinite number of functions, so it still holds. Even if we have an integral here, right, integral outside instead of different functions, we still have this nice property, right? So the linearity can be extended to any case, okay? So that's linearity. And then we talk about the following topics, right? So yeah, we see the Fourier transform of a non-periodic signal, and then we talk about how about we're passing through a non-periodic signal in an LTI system, right? Which meaning that we're passing through an energy signal to an LTI system. And then we talk a little bit about the negative frequency, right? And the reason we talk about that is that so negative frequency is kind of weird, right? But for real signal, it does not have any physical meaning, so it's just a mathematical effect, right? And then we talk about the common Fourier transforms, and then we didn't have the time to talk about the frequency shift property yet, so we're going to talk about it today. Okay, and so now let's denote S as an energy signal, and then its Fourier transform is S of F, and then we're passing through an S into a LTI system, and the impulse response is denoted by h of t, and its Fourier transform is denoted by h of f. And here is what is really happening. So basically, because our system is an LTI system, so passing through a signal through an LTI system is convolution, right? So convolution between the input signal and system, and then we get output, right? After some manipulation here, so we went that in detail in the last lecture. So basically, what we got is as follows, right? So in the frequency domain, our output signal is a multiplication between the system impulse response times the signal itself, okay? So this basically meaning that in the frequency domain, the operation is much simpler, right? Instead of convolution, and we only need to do a multiplication, so, right, which is a much simpler operation in general. Okay, so this is very nice. And then for the negative frequency, so you can read the book to explain, what kind of the meaning, mathematical meaning of the negative frequency. But here we see an example. So when the signal denoted by g of t, so that's a real signal, so we can have the following relationship, right? So g minus f naught equals to g f naught conjugate, right? So this basically means that the negative frequency component does not carry any additional information, right? Because so if we know g f naught, we know g minus f naught exactly, right? So basically, again, so this is a mathematical effect for at least for the real signal, so we don't need to worry too much about it, okay? And so if we consider, this g of t, that is part of a periodic signal, and then if we do this Fourier series synthesis equation, and we can see that by adding these two components, the real part and the positive part and the negative part, then we get a real part, right? So we don't have the imaginary part anymore, so which makes sense, right? Because GT is real signal. Okay, so that's just some intuitive explanation of the negative frequency. So that's a mathematical effect. Okay, and yeah. And when we measure the bandwidth, we may only care about the real part of signal in the frequency domain, okay? And for the common Fourier transforms, so here we'll emphasize a lot on the direct delta signal, okay? If we do a Fourier transform of a direct delta signal, we get 1, right? Which kind of makes sense, right? Because the direct delta signal meaning that we have a very big jump in the time domain, right? So it's from 0 to infinity at no time, right? In order to describe this behavior, so in the frequency domain, so we need all the frequency components with equal amount, right? So this is a mathematical effect, but it sort of makes sense, okay? And in terms of a system, right? When the system impulse response is a delta t, so this basically means that in the frequency domain, it is just 1, right? 1 basically means that nothing happened, right? Because the output equal in the frequency domain, the output equals to the input multiply the system, which is 1. It means nothing happened, right? So which kind of makes sense. All right, and then if we shift delta by f naught, so basically what we get is a complex exponential, right? So this is a very nice relationship between the direct delta signal, and the complex exponential signal. Today we're going to see other, maybe more non-intuitive relationship between these two guys, but there are a lot of relationship between delta and the complex exponential, right? They are kind of, how to say it? I cannot say they are the same, but they are extremely related. We can use the delta signal to represent complex exponential and vice versa, okay? And that is the fundamental reason why we can do Fourier transform for some periodic signals, okay? So this is very nice, and because of this, so yeah, we can immediately see that we can do Fourier transform for cosine signal, okay? Yeah, because cosine signal, by using the Euler formula, we can see cosine signal equals to this, right? So this guy, the Fourier transform of this guy is this guy, and the Fourier transform of this guy is this guy, right? And by doing this, we can see the Fourier transform of cosine signal is nothing but just this guy. Okay, by introducing delta signal, we can do Fourier transform for periodic signals. Okay, so actually a lot of periodic signals that we use in practice can have Fourier transform, right? So normally in practice, we don't use much Fourier series, we just use Fourier transform. Okay. So that is very nice. So if you can do the Fourier transform for delta for cosine, then we should be able to do that for sine as well, right? Because cosine and sine, they are extremely related. So here we can, by using, again, the Euler's formula, we can write down the sine signal look like this. Again, so here, instead of summation, so we compute the difference between, the j has to be here, so I think there's a typo. So we can compute the difference between two complex exponential, and then normalize it by 2 times j instead of 2, right? And by doing this, again, so we don't, the Fourier transform of this guy is this guy, and Fourier transform of this guy is this guy, right? And then we could have the Fourier transform of sine signal is nothing but, again, so we can use the delta signal to represent the Fourier transform of a sine. Okay, so that's pretty nice. Yeah, any questions so far? Okay, and then here, so based on that, we can also see that, so what if in the time domain we use a signal multiply a complex exponential, right? And you can solve this using the sine and cosine as well, right? Doesn't matter. So you can try it at home. So, but here what I did is just compute this guy directly, right? So if we compute that, we can have this is our signal, and then multiply this part with the integral. So that's the definition of the Fourier transform. Okay, and then what we do here is that we just combine these two together, right? We have f minus f naught, and we take the minus sign out, right? And this is the definition of the Fourier transform of this guy, but the frequency component is shifted by f naught, right? So this basically means that if in a time domain we have a phase shift, right? Normally, if we times a complex exponential, we call that a phase shift. And in the frequency domain, we have a frequency shift. Okay, and this is super nice and important. Okay, very good. All right, and yeah, and we can extend it, right? So, for example, if we times cosine instead of complex exponential, so we expand cosine by the summation of two complex exponential. Right here it's like now we shift this guy to the left, add shift this guy to the left, and add shift this guy to the right. Okay, we have like two double-sided signal, right? So before, if we use complex exponential, we just have one side. But now if we use cosine, so let's say here is our original signal GF, right? After multiply this by cosine in the time domain, so in the frequency domain, what is happening is that, so let's say here is 1, then we have 2 of this exact same shape, right? But the magnitude is half now. Okay, and here we have f naught, and here we have f minus naught, right? So this is what we get. Okay, so why this is kind of useful? So the reason is that, so in practice, how can we implement this behavior, right? So in practice, we don't have anything complex, right? Everything's real, right? How can we use a real signal multiply a complex exponential? Is there a trivial way to do that? Right? It turns out that we can still do that, but we need some mathematical tricks. Okay, but if we do this, it's very easy, right? We just multiply the original signal by a cosine signal, and then we can do this kind of shifting. And as what we said, right? This part does not carry any useful information, right? We don't need to care about that, right? Only this part is useful. Okay, so that's the easy way to implement this so-called modulation in practice. Does that make sense? Okay, it's kind of fast, but we're gonna visit this back later. All right, okay, I think that's the end of the last lecture. So we didn't cover this in the last lecture, so we'll cover it now. All right, okay. yeah, today we have something more interesting to cover. Okay, yeah, so today, so we have two topics. So the first topic is, so now we have learned the Fourier transform and also the Fourier series, right? And we say, okay, Fourier series is for periodic signal, and the Fourier transform is for non-periodic signal. And then we say, okay, wait a minute. We can still do Fourier transform for some periodic signal, okay? So it's kind of messy, right? So today we're going to see, a more clear relationship between these two guys, okay? So first of all, we're going to see what is the relationship is Fourier transform and the Fourier series. Basically, we want to connect Fourier transform to and Fourier series. Okay, so in other words, so we're going to see how we can use Fourier transform to compute Fourier series. Okay, so it's just a purely mathematical effect, and we don't have much physical meaning there, but we're going to see how we can do that. And the other thing is that how exactly we can compute the Fourier transform for periodic signals, right? So we have seen for sine and cosine, but in general, how should I do that? How should I do that, right? Second is the Fourier transform of a periodic signal, right? Okay, great. And let's see, number one, how can we use Fourier transform to compute Fourier series? Okay, any idea? So what did I mean for that? Actually, the idea is very clear. Okay, it's not that hard, but let's see an example, okay? So we consider a specific signal, let S of t be a periodic signal. Okay, and we write S of t as the follows: a summation of this. Yeah, for simplicity, we just assume that the form of G is nice. Okay, so it's something like this. Yeah, you can have the general form of G, but here I just assume that GT is like this. Okay, so it has a finite length. Okay, so we assume that the length of the signal is tau. Yeah, this is how I write tau, right? So which is a Greek letter for t, in my opinion. Okay, and they will assume that so here so we shift this guy by t naught to everywhere, right? We have a t naught here, and we have 2t naught here, and so on. And on the negative side, we have the same thing, right? And I have minus t naught and minus 2t naught, okay? So this is what we got. And this signal, this periodic signal, so we have dot, dot, dot here. So this is our S of t, okay? And clearly, so this is t naught, and the length is tau, right? We assume tau is less than t naught. Okay, so what if tau equals to t naught? What will happen? Let's assume this signal is symmetric. Okay. Right. What if tau equals to t naught? So what the signal will look like? Yeah, imagine. Right. So this length is t naught, and this length is tau. This length is tau. Right. So basically, this means that this length is tau half. Right, and this length is tau half, right? So this plus that equals to tau. So what if tau equals to t naught? What will happen? Yeah. Yeah, it'll be a straight line, right? Because so these two has to move much closer to each other, right? So basically, we're gonna have something like this. So here's 0, here's tau over 2, and then it will be consecutive, right? The length of this is t naught over 2, right? And then so on, right? It will be a just straight line, okay? Yeah, so basically, yeah, that's how we define this, right, for simplicity. All right, so clearly this is a periodic signal, right? And we can compute the Fourier series for that, and we did that in class, right? At least in the slide. Okay, so let's compute the Fourier series of that. And then we're going to see how we can use Fourier transform to compute the Fourier coefficient, right? So hopefully you still remember the formula of the Fourier series, right? We denote that by S of n here, right? Who will still remember the formula to compute the Fourier series? Yeah, what's our formula? So nobody remembered? Yeah, let me give you a hint, right? So we have 1 over t naught, so which is fundamental period, right? And then we do an integral. And then we use S of t times what? Complex exponential, right? So what is here? Say it louder. J omega meaning 2 pi n f naught t, right? So I have minus sign here. Don't forget the minus sign. So this is the analysis equation or the forward transform, right? For the forward transform, we always have a minus sign here. So that's very important. Okay, so did that ring any bell? Okay, yeah, just try to remember this, right? Because we're going to use this all the time in this class, but for the Fourier transform, not for Fourier series. But you know, this kind of formula, we use that all the time. But if it's an inverse transform, we don't have this, right? We just have a plus sign here, and then we switch this to here, and then change the integral to a summation, right? But don't need to remember here is the integral summation, right? Just do whatever you can, right? Because for Sn, you cannot do integral over Sn, right? Because it's discrete. We can only do summation. Okay, don't need to remember too much about it. Okay, so, okay, let's see what does that mean, right? So here, basically, so the integral limit is from minus t naught over 2 to t naught over 2, means that we do the integral over just one fundamental period, right? So here, we just need to do the integral from, here is minus t over 2, and here is t naught over 2, right? We just need to do the integral from here to here. Okay, so this is our integral limit. And within the integral limit, we just have our function g of t, right? So this means that we can comfortably write, so this is our integral limit, g of t, e minus j, 2 pi n f naught t dt, right? That clear? Right. Okay, great. So now let's see. So this is a function of gt now, right? And the gt is what? It's not periodic, right? You will see, yeah, the g of t just defined in this way, right? And this is a shifted version of gt, right? This guy is gt minus t naught. This guy is gt minus 2t t naught. And this guy is gt plus t naught. okay, and so on, right? So this is just the GT, okay? So it's not periodic, okay? So for non-periodic signal or aperiodic signal, we cannot do Fourier series. We can do Fourier transform, right? So let's compute the Fourier transform of GT, okay? So we have GF. So hopefully you remember the formula for the Fourier transform. Right? For the Fourier transform, we don't have this scaling factor here because we don't have T naught, right? And then the integral limit would be like this. We do from minus infinity to plus infinity. And then we have exactly the same format, right, compared to this. GT E minus J 2 pi. No n times F naught anymore, right? We don't have fundamental frequency. We have a continuous F T dt, right? So this is the Fourier transform, right? Okay, great. Now let's compare these two, right? So let's compare this and this. So what can you find? Right? So basically, what does this guy equals to? So can you represent this guy by GF? Right? Because GT is just this part, right? Outside of T naught over 2 or T naught over minus T naught over 2 or T naught over 2, they're all 0. Or precisely, we just need to do the integral between these 2 points, minus tau over 2 to tau over 2, right? Yeah, so this basically means that we can, where is the other eraser here? So we can change the limit of the integral to T naught over 2 or minus T naught over 2, right? So now let's compare the two. What are the difference? So can you represent this guy using GF? Can you? Yes?
Yeah, if you set F equals n times F naught.
Exactly, right? So the only difference here is this guy, n times F naught, and the F here. So we just replace F by n F naught, and then we're done, right? Yes?
And the scaling factor?
Yeah, very good. Yeah, we cannot forget it, right? Okay, so very good comment. So basically, we're not done yet, right? So we just replace this part by using this guy. And this is what? Is the Fourier transform. Okay, so we use the Fourier transform now to compute the Fourier series now. Okay, to summarize, so this guy, eventually, that will equals to, or let's write this way, Sn equals to, so we still have this factor here, right? 1 over T naught, and then use G of F naught, or if we like, so we can write it in several ways, right? So N over T naught, or this guy equals to F naught G N F naught. Okay, so pick the way that you like. Okay, so it means that the Fourier series coefficients can be computed using the Fourier transform of the signal in one period. Right? It's a purely mathematical effect, right? So does that make sense? Right? So, so it basically means that in order to compute the Fourier coefficients, Fourier series coefficients, you don't need to really compute it, right? You just need to pick, get rid of other periods, just pick one period, and then compute its Fourier transform, and replace F by n times F naught, and then add the scaling factor in front. Then you can get the Fourier series. Right? Does that make sense? Sounds good? Okay, yeah, that's the first part, right? So we can use the Fourier transform to compute the Fourier series. Okay, so let's see a concrete example. Yeah, I shouldn't remove this, but let me draw it again. So still consider this kind of signal, okay? And with the same parameter, let's say. Okay, so let's say here is 0, and we have tau over 2, minus tau over 2, and here is t naught. Okay, so basically, I want to introduce you. So what is GF look like, right? So this is a very common and often used signal in communication system. It's a square wave, right? So basically, this guy, that's our GT, right? So in practice, so what we do is that we denote this guy using this signal. It look like a pi, but I'm not sure it's a pi or not. We mimic this shape, and we have this letter. Probably it's a, I don't know, big pi or whatever. So we call that the unit rectangle signal. Okay. Unit rectangle signal. And the reason we call that unit, meaning that, so the definition of it is as follows. So it is 1 when the absolute value of t is less than or equal to half. Okay, and it's 0 otherwise. Okay, so basically, when we say it's a unit rectangle, it has something like this, right? Here's 1, here's half, here's minus half, right? So that's the unit rectangle signal. Looks like that. Okay, so this is our S of t, right? And this is our G of t. So in order to compute Sn here, so we just need to compute the Fourier transform of G of f, right? Let's see how we can compute it. Yeah, well, we're going to compute it here. First of all, let's write down GT. Yeah, let's assume that the magnitude here is just 1, right? So now let's write GT in terms of this guy, right? So the difference here is that for GT, so here is half, here is tau over 2. Okay, everything otherwise they are identical, right? How can we represent GT in terms of the unit rectangle signal? Right, you just need to either multiply tau or divide it by tau, right? So what should we do? We either use t multiply or divided by tau. So which one we should use? How can we determine that? So it's like either g multiplied tau or divided by tau would be equal to half, right? And t is this guy, right? Therefore, it's tau over 2 divided by tau equals to 1 over 2, right? Basically means that when you just use t divided by tau. Okay, so if this method doesn't work for you, you just give tau a value. For example, what if tau is 2, right? So this guy is wider, right? And then we want to use this guy to represent this guy, so we need to make something wider. Make something wider meaning that we need to divide it by this, right? So that's how to manipulate a signal. Okay, and this is how we use this unit rectangle to represent the G of t, right? And so now let's compute the Fourier transform, GF. Okay, so that's the Fourier transform of this guy. Okay, so basically now we write down again the definition of it. Okay, so this is this guy, E minus J 2 pi ft dt. Okay, so because the definition of this guy, so this guy look like this, right? So basically, integral limit will becomes, right, just like this much, right? So the integral limit is from minus tau over 2 to tau over 2. And then the value of this guy within this range is nothing but just 1, right? And then we have e minus j 2 pi ft dt. Okay, so let's continue here. So remember this, right? So we're gonna, maybe just remember this. Yeah, one of the eraser is much easier to use than the other one. So I just, okay. Great. Okay, let's continue. So that is nothing but, so we need to do this integral, right? Hopefully everybody knows how to do this integral, right? How to do that? What does that equal to? Tell me. We should have this part, right? Evaluate at tau over 2 minus tau over 2, right? And then we'll have a coefficient in front, right? Just need to divide this part, right? That makes sense? So this is the integral of complex exponential, right? So just need to move this part into the denominator. And then we got jf. And then inside is minus e minus j 2 pi f. We need to, so need to replace t here, right? It's tau over 2 minus e j 2 pi f, and times minus tau over 2, right? So that's what we get. Yeah, we do some simplification, right? And we cancel this 2 here, and then we get e minus j 2 pi f tau, or no 2, right? 2 is canceled. Pi f tau minus e j 2 pi, no 2, sorry. J pi f tau, right? We cancel the 2, and we'll have a minus sign here. Right? Yeah, something is, we have a minus sign here, right? So, yeah, we don't have a minus sign here. Hopefully that makes sense. Yeah, is my computation correct? Should be, right? Now let's do some manipulation. So we move this negative sign inside. So we have this. And then let's see what we're going to do here, right? So because we move the negative sign inside, we have this e j f tau minus e minus j pi f tau, right? So this is what we get. So when you see this, what do you think? We have a difference between two complex exponential. Can we simplify it? Right? Consider Euler's formula, right? So the difference of the complex exponential, and here's the plus, here's minus, right? It's related to sign, right? So remember that. So we need to, if we divide it by 2j, so this will give us a sign signal, right? And then since we divided by 2j here, so we need to multiply 2j back, right? And we'll have 2j here, and we'll have a 2j here. I'll cancel this 2j. And see here, what we have is 1 over pi f. And then this guy is nothing but a sign. Oh, I copied it wrong, right? We don't have this 2. Sine pi f tau. Right? It's pretty simple. Does that make sense? Everyone? Okay. So if that makes sense to you, so basically, and you can see that, this guy and this guy looks pretty similar, right? The only difference is that we don't have a tau here. Okay, so let's make them the same, see what will happen. Right, so basically, what I want is a sine pi f tau divided by pi f tau. And then we have to multiply tau in front, right? Because we need to make them equal. And what is that? So anybody know this function? Not seen this before? Yeah, it's an extremely important function. We have a special name for it. Yes?
The sync function?
Exactly. It's a sync function. Okay, that equals to SINC, it's called sinc, pi f tau. Okay, so the definition of the sinc function, I say sinc of x equals to sine x over x. Okay, so that's the definition of a sinc function. So this is extremely important. Okay, in communication. Okay, so again, so we're going to see that in the very end of our class. So this is a waveform we use for 4G, 5G, and 6G, whatever, on the Wi-Fi 6 and 7. So this is what we use in practice. Okay. Okay, but in the time domain, it's very simple, right? In the time domain, just square waveform. Okay, in the frequency domain, it's a so-called sinc function. Okay, great, and we're done, right? So basically, we know we can rewrite this, right? From all of this effort, we know GF. So that's nothing but tau times sinc pi f tau, right? So this is the Fourier transform of a sinc function. Okay, so let's draw this, right? Let's see what does this function look like, right? Because it's a sine signal divided by a linear function, right? So when x goes to become larger and larger, right, the magnitude has to become smaller and smaller, right? So we know the trends of the signal, right? When x goes to infinity, this has to go to 0, right? But the non-trivial part is what if x is small, right? What if x is close to 0? So what does that equal to? How can I compute it? Right, when x is 0, so in the numerator is 0, in the denominator 0 again. So that is what? 0 over 0. So to compute it, we need to use L'Hopital's rule, right? We just do a derivative of it, and then do a derivative of it, right? Derivative of x is 1. Derivative of sine is cosine. Cosine 0 is 1. Therefore, at 0, this function equals to 1. Okay, but we need to multiply tau in front. So at 0, this is tau. Okay, and then the rest is kind of simple, right? And then, so this has to decay, and it will reach 0 at some point, right? Because sine will reach 0 at some point, right? So, and then, so this will look like this, and then the magnitude will become smaller and smaller. And actually, it's easy to check this is an even function, right? It means that it is symmetric around the y-axis and so on. So this is how this function looks like. Okay, it's a very nice, very beautiful function. And so can you tell me what is this point, this 0 crossing point? Right, so that's the first time it is equal to 0. Basically means that, so when it's the first time sine x equal to 0, when x is, right, sine x look like this, right? So when it crosses 0 in the first time, so that equals to pi, right? Then we just let inside equals to pi. Then we can see f tau has to equals to 1. Then f equals to 1 over tau, right? So this guy is just the 1 over tau. Okay, right? And then when is the time, so this guy cross 0 again. So that's when x equals to 2 pi, right? So then that will be 2 over tau and so on. And similarly, so here's minus 1 over tau. Here's 1 minus 2 over tau, and so on. Okay, and this is how the g of f look like. Okay, so now let's get back to our original question, right? So now we know gf, okay? And then how can we get Sn here, right? Sn is nothing but we use 1 over t naught, right? Just ignore that. And then we just need to compute the point at nf naught, okay? So basically, when n is 0, so we have this point, right? And probably, yeah, because know that, so we have a very important constraint here we didn't emphasize. So here we have to assume that t naught is bigger than tau, right? Otherwise, they just touch each other, right? Yeah, we say when t equals tau, so it will be connected, right? So under that assumption, so basically, so 1 over t naught will be less than 1 over tau, right? So basically, we have this is 1 over T naught, and we have another point probably, so that is 2 over T naught, and so on, right? Does that make sense? Okay, so and on the negative side, it will look like this, right? Probably it will look like this, and so on, right? And all of this, you know, it is basically this part, right? G and F naught, and if we multiply that by 1 over T naught, you're gonna get the Fourier coefficients, right? Does that make sense? Okay, to emphasize a little bit, so this zero crossing point is extremely important in practice. Okay, so yeah, we can write it as k over tau, where k are all the integers. Okay, let's just see special example of it. So let's see a special case. So when T naught equals to 2 times tau, so what will be the coefficient look like? The Fourier coefficient look like? Right, again, it will be like this. Right, so when T naught equals to 2 times tau, so this basically means that 1 over tau equals to what? 2 times T naught, right? So this basically means that, so for this guy, G and F naught, so we still have this point, and then we have this point. So that's 1 over T naught, and the 2 over T naught equals to 1 over tau, so we have this point, right? Similarly, and we have this point, and this point, this point, and this point, right, and so on. Right, so we just need to take all of this point out, so that will give you G of F and naught. Yeah, does that make sense? Okay, so we don't have time to cover the second part, so we're going to cover that in the next lecture. Okay, so, any questions? So if no, so I will try to upload the video better we can. So have a good weekend. See you next time.